future space technologies that will change everything. For as long as humanity has looked up at the night sky, one question has echoed across generations: are we alone in the universe? In recent decades, science has taken a dramatic leap forward. Astronomers have now identified thousands of planets orbiting stars beyond our solar system. Some of these distant worlds may have the right conditions for life: liquid water, stable atmospheres, and chemical signatures such as oxygen and methane that could hint at biological activity. At the same time, the way we travel through space is undergoing a quiet revolution. Traditional rockets rely on short, explosive bursts of power, much like flooring a car's accelerator and then coasting with the engine turned off. New propulsion systems reverse that logic. They apply a small but continuous force over long periods, gradually building extraordinary speeds. Operating entirely in space, these systems act like tugboats, attaching to spacecraft and steadily pushing them toward destinations such as the Moon, Mars, and even the outer planets. Equally transformative are new ideas for returning to Earth. Instead of fiery reentries and ocean splashdowns, emerging concepts envision reusable space planes that land smoothly on runways, closing space missions with the elegance of an aircraft landing at an airport. Together, these technologies may finally give humanity the tools needed to explore distant worlds and perhaps discover life beyond Earth. Humanity is standing at a turning point in the history of exploration. For thousands of years, the stars were unreachable mysterious points of light that inspired myths, religions, and unanswered questions. Today, they are becoming destinations. Over the past 30 years, advances in astronomy, propulsion, materials science, and artificial intelligence have quietly set the stage for a transformation that could redefine our understanding of life, civilization, and our place in the universe. This transformation did not happen overnight. It began in the late 20th century with the first confirmed discoveries of exoplanets, planets orbiting stars beyond our Sun. Since then, space telescopes have revealed worlds with clouds, weather systems, and chemical compositions that suggest oceans and potentially life-supporting environments. At the same time, engineers realized that chemical rockets alone would never be enough to make deep space exploration practical, affordable, or sustainable. Why does this matter now? Because the technologies once considered science fiction are rapidly becoming engineering realities. Electric propulsion systems capable of running for years, reusable space planes designed to fly like aircraft, and autonomous spacecraft that can navigate without constant human input are no longer theoretical. They are being tested, refined, and prepared for deployment. How will these technologies change everything? They will shorten travel times, reduce costs, expand human presence beyond Earth, and dramatically increase our ability to search for life elsewhere. More importantly, they will shift space exploration from rare, heroic missions into a continuous, evolving enterprise. This is not just a story about machines. It is a story about patience, precision, and ambition, and about a future where the question, "Are we alone?" may finally have an answer. The ancient question, "Are we alone in the universe?" For as long as human beings have been able to think abstractly, we have wondered whether we are alone. Long before telescopes, before science, before even written language, early humans looked up at the night sky and sensed that it was vast, ordered, and somehow meaningful. The stars did not merely decorate the darkness, they provoked questions. Were they lights? Holes in the sky? Homes of gods, spirits, or other beings? And if the universe was so immense, why would life exist only here? This question, "Are we alone in the universe?" is not a modern curiosity. It is one of humanity's oldest intellectual and philosophical problems. What has changed over time is not the question itself, but our ability to approach it with evidence rather than imagination alone. Early philosophical roots. In ancient Greece, philosophers were already debating the possibility of other worlds. Democritus, in the 5th century BCE, argued that the universe contained countless worlds, some similar to Earth and others very different. Epicurus went further, suggesting that it would be irrational to assume that Earth was the only place where life could arise. To him, nature operated by universal rules, not exceptions. In contrast, Aristotle believed Earth was unique, a privileged center of a carefully ordered cosmos. His view dominated Western thought for nearly 2,000 years, reinforced later by religious interpretations that placed humanity at the center of creation. For centuries, the idea of other inhabited worlds was not just scientifically unsupported, it was often considered heretical. Yet even during those long periods of intellectual constraint, the question never disappeared. It survived in literature, in quiet philosophical debate, and in humanity's persistent fascination with the sky. The Copernican shift, humanity loses the center. Everything changed in the 16th century with Nicolaus Copernicus. By proposing that Earth was not the center of the universe, but merely one planet orbiting the Sun, he initiated what is now called the Copernican revolution. This was not just an astronomical correction, it was a psychological shock. If Earth was not the center, then perhaps humanity was not cosmically special either. Later, Galileo's telescope revealed that other planets had moons of their own, that Venus showed phases like the moon, and that the heavens were not perfect or unchanging. These discoveries quietly undermined the idea that Earth was fundamentally different from other celestial bodies. By the time Isaac Newton described universal laws of motion and gravity, a powerful implication emerged: the same physical rules applied everywhere. If the laws of nature were universal, then the processes that produced life on Earth might not be unique. This idea that Earth is not special in its physical makeup became known as the principle of mediocrity. It does not claim that Earth is unimportant, but rather that it is not an exception to cosmic rules. From speculation to science. For most of history, the question of extraterrestrial life remained philosophical because there was no way to test it. That began to change in the 20th century. The development of modern astronomy revealed that our galaxy alone contains hundreds of billions of stars. Later observations showed that there are hundreds of billions of galaxies in the observable universe. The sheer scale of the cosmos forced a reassessment of probability. If life arose on Earth relatively quickly after conditions stabilized, could it really be a once-in-the-universe event? In 1961, astronomer Frank Drake attempted to frame the question scientifically. He introduced what is now known as the Drake equation, a probabilistic formula designed not to give a final answer, but to structure thinking. The equation considered factors such as the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the likelihood that life becomes intelligent, the duration such civilizations might exist. At the time, most of these variables were complete guesses. Critics argued that the equation produced no real knowledge. But Drake's contribution was profound. He transformed a philosophical question into a scientific one. For the first time, "Are we alone?" became a problem that could, in principle, be measured. The Fermi paradox: where is everybody? As estimates of habitable planets grew more optimistic, a troubling contradiction emerged. Physicist Enrico Fermi famously asked a simple question during a lunchtime conversation in 1950, "Where is everybody?" If intelligent life is common, and if technological civilizations can spread through the galaxy over millions of years, a short time on cosmic scales, then evidence of their existence should be obvious. Yet the universe appears silent. This contradiction is known as the Fermi paradox. It does not prove that extraterrestrial life does not exist, but it highlights a gap between expectation and observation. Over time, scientists and philosophers proposed many possible explanations. Intelligent life is extremely rare. Civilizations tend to destroy themselves. Advanced species choose not to communicate. We are looking in the wrong way. We are early in the cosmic timeline. Each explanation carries profound implications. Some suggest hope and patience. Others suggest fragility and danger. Importantly, the Fermi paradox reminds us that finding life is not just about biology, it is about technology, sociology, longevity, and survival. Life as we know it and life as we don't. Another major shift in thinking came from biology itself. For much of modern science, life was assumed to be fragile, requiring narrow conditions, moderate temperatures, liquid water, sunlight, and a stable environment. Earth seemed exquisitely balanced. Then came the discovery of extremophiles, organisms that thrive in conditions once thought lethal. Life was found deep beneath the ocean floor, inside acidic pools, near volcanic vents, and in frozen tundra. Some organisms survive intense radiation, crushing pressure, and near boiling temperatures. These discoveries expanded the definition of habitability. Life, it turned out, is not as delicate as once believed. This realization had a direct impact on astrobiology. If life can adapt to extreme environments on Earth, then other worlds once dismissed as hostile might also be viable. Moons like Europa and Enceladus, with subsurface oceans beneath icy shells, suddenly became compelling candidates in the search for life. The question shifted again, not whether life could exist elsewhere, but how different it might be. Technology enters the search. The second half of the 20th century introduced technologies that directly targeted the question of extraterrestrial intelligence. Radio astronomy made it possible to search for artificial signals patterns that could not be explained by natural processes. Projects such as SETI, Search for Extraterrestrial Intelligence, began scanning the skies for narrowband radio transmissions. The logic was simple: radio waves travel long distances efficiently, and any technologically advanced civilization might use them, intentionally or unintentionally. So far, no confirmed extraterrestrial signal has been detected. However, this absence does not mean failure. It means the search space is enormous. Humanity has sampled only a tiny fraction of possible frequencies, directions, and time scales. In cosmic terms, we have barely begun listening. More recently, scientists have expanded the search beyond radio signals to include laser emissions, unusual energy signatures, and even large-scale engineering projects, so-called techno-signatures, that might reveal advanced civilizations indirectly. Psychological and cultural impact. The question of whether we are alone is not just scientific, it is deeply personal and cultural. If we discover microbial life elsewhere, it would confirm that life is a natural outcome of chemistry, not a miracle. If we discover intelligent life, it would redefine humanity's place in the universe more dramatically than any previous scientific revolution. Religions, philosophies, political systems, and cultural identities would all be forced to adapt. Some scholars argue that humanity is not psychologically prepared for such a discovery. Others argue that the idea has been so thoroughly explored in science fiction and media that the shock would be less severe than imagined. Still, the implications are enormous. Knowing that we are not alone could foster humility and cooperation, or fear and competition. It could unite humanity or deepen divisions, depending on how the discovery unfolds. Why this question matters now. What makes this moment different from all previous eras is not curiosity, but capability. For the first time in history, we possess the tools to detect planets around other stars, analyze the chemical composition of distant atmospheres, search for biological and technological signatures, send probes to ocean worlds within our own solar system. The ancient question is no longer trapped in philosophy. It is entering the realm of experimental science. And this is where future space technologies become critical. Without new propulsion systems, power sources, and autonomous spacecraft, the search for life will remain slow and limited. With them, it accelerates dramatically. This part of the story sets the foundation. Before engines, before space planes, before deep space missions, there must be a reason to go, to look, to listen, to explore. That reason is simple, profound, and timeless. We want to know whether the universe is silent or whether it has been speaking all along, waiting for us to learn how to hear it. Exoplanets and the search for habitable worlds. For most of human history, the night sky appeared deceptively simple. Stars seemed fixed, eternal, and solitary, each one a distant sun, perhaps, but imagined without companions. The idea that stars might host planets of their own was intuitive to philosophers, yet frustratingly beyond proof. Even as late as the mid-20th century, astronomers could not say with confidence whether planets were common or rare. Were planetary systems like our own the rule, or the exception? Today, that question has been decisively answered. Planets are everywhere. The discovery of exoplanets, planets orbiting stars beyond our solar system, has transformed astronomy more radically than almost any development since the invention of the telescope. It has also reshaped the search for life in the universe, shifting it from speculation to statistical inevitability. The first confirmations, a quiet revolution. The modern exoplanet era began in the early 1990s, not with fanfare, but with cautious excitement. In 1992, astronomers detected planets orbiting a pulsar, the dense, rotating remains of a dead star. These worlds were strange and hostile, but their existence proved one thing unmistakably: planets could form in unexpected places. The real breakthrough came in 1995 with the discovery of 51 Pegasi b, the first confirmed planet orbiting a Sun-like star. This planet defied expectations. It was a hot Jupiter, a gas giant orbiting extremely close to its star, completing a full orbit in just 4 days. According to prevailing theories, such planets should not exist. Rather than undermining the field, this discovery opened it. If nature could produce planetary systems so different from our own, then the universe was far more creative than previously imagined. Within a decade, dozens of exoplanets were confirmed. Then hundreds. Today, the count exceeds several thousand, with thousands more candidates awaiting verification. The question is no longer whether planets exist elsewhere. It is how many of them could support life. How we find other worlds. Exoplanets are extraordinarily difficult to detect. They are faint, small, and lost in the glare of their parent stars. Astronomers rarely see them directly. Instead, they rely on clever indirect techniques, methods that read subtle distortions in starlight like fingerprints. The most productive method so far is the transit method. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of the star's light. By measuring these periodic dips in brightness, astronomers can infer the planet's size, orbital period, and distance from its star. NASA's Kepler Space Telescope, launched in 2009, used this method to stare at a single patch of sky containing over 150,000 stars. Its results were astonishing. Kepler revealed that planets are not rare outliers, they are a standard outcome of star formation. Another key technique is the radial velocity method, which measures the slight wobble of a star caused by the gravitational pull of an orbiting planet. This method provides estimates of planetary mass and helps confirm discoveries made via transits. More recently, astronomers have begun to use direct imaging, gravitational microlensing, and advanced spectroscopy. Each technique adds another piece to the puzzle, allowing scientists not only to detect planets, but to characterize them. The diversity of exoplanets, a universe of extremes. One of the most surprising outcomes of exoplanet research is how diverse planetary systems are. Our solar system once seemed like a template. It is now clear that it is only one arrangement among many. Astronomers have identified hot Jupiters, gas giants orbiting dangerously close to their stars. Super-Earths, rocky planets larger than Earth but smaller than Neptune. Many Neptunes, with thick atmospheres and unknown surfaces. Rogue planets, drifting through space without a star. Tidally locked worlds, where one side permanently faces the star. Some planets have years lasting only hours. Others orbit 2 or even 3 stars. Some are scorched by extreme radiation, others are frozen in perpetual darkness. This diversity forces scientists to rethink habitability. Earth-like conditions may not be the only path to life. However, they remain our best starting point. The habitable zone, a useful but limited concept. Central to the search for life is the idea of the habitable zone, often called the Goldilocks zone. This is the region around a star where temperatures could allow liquid water to exist on a planet's surface, neither too hot nor too cold. Water is not assumed to be magical. It is assumed to be practical. On Earth, water acts as a universal solvent, enabling complex chemistry and stable biological processes. Until proven otherwise, it remains the best guide for identifying life-friendly environments. But the habitable zone is only a first filter. A planet can orbit within this zone and still be utterly uninhabitable. Atmospheric composition, magnetic fields, geological activity, and stellar behavior all matter. For example, red dwarf stars, the most common type in the galaxy, often produce intense stellar flares that could strip atmospheres from nearby planets. Yet they also live for trillions of years, providing long-term stability. Again, the universe resists simple rules. Earth-like worlds, how common are they? One of Kepler's most significant contributions was enabling astronomers to estimate the frequency of Earth-sized planets in habitable zones. While uncertainties remain, current data suggests that such planets are not rare. In our galaxy alone, there may be tens of billions of potentially habitable planets. This estimate does not mean that these worlds are inhabited. It means that the conditions necessary for life, at least as we understand them, may be widespread. This realization marks a psychological turning point. The search for life is no longer about finding a cosmic anomaly. It is about identifying which of many possible worlds cross the threshold from chemistry to biology. Atmospheres, reading the breath of distant worlds. The next frontier in exoplanet science is atmospheric analysis. When a planet transits its star, a small fraction of starlight passes through the planet's atmosphere before reaching Earth. This light carries chemical signatures, absorption lines that reveal what gases are present. Scientists can now detect water vapor, carbon dioxide, sodium, and even complex molecules in some exoplanet atmospheres. Future instruments aim to identify biosignatures, gases like oxygen or methane that, on Earth, are strongly associated with life. However, interpretation is delicate. Non-biological processes can also produce these gases. A convincing detection of life will likely require a combination of indicators, not a single signal. This is where caution meets excitement. The tools are becoming powerful enough to tempt bold conclusions, but science demands patience. Famous worlds and nearby hope. Several exoplanetary systems have become landmarks in the search for habitability. The TRAPPIST-1 system, located about 40 light-years away, contains 7 Earth-sized planets, 3 of which lie within the habitable zone. Their compact arrangement allows scientists to study them in remarkable detail. Proxima Centauri b, orbiting the star nearest to our Sun, is another compelling candidate. While its environment is likely harsh, its proximity makes it a prime target for future missions. These worlds are not destinations in any practical sense, at least not yet. But they are laboratories. They allow us to test models, refine techniques, and imagine futures where interstellar exploration is no longer purely fictional. Why exoplanets changed everything. Before exoplanets, the search for life was constrained by a sample size of 1. Earth was our only example. Today, we have thousands of data points and counting. This does not guarantee that life exists elsewhere. But it transforms the question from "is it possible?" to "where should we look first?" And that shift matters. It drives funding decisions, mission designs, and technological priorities. It motivates the development of more powerful telescopes, advanced propulsion systems, and autonomous probes. It turns curiosity into strategy. In the next part of the series, we will move deeper from planets themselves to the elements that make life possible. Water, atmospheres, and chemical signatures are the quiet storytellers of the cosmos, and learning to read them may be the key to answering humanity's oldest question. Water, atmospheres, and chemical signs of life. If planets are the stage, then chemistry is the script and water is often the opening line. When scientists talk about the search for life beyond Earth, they return again and again to a short list of ingredients: liquid water, a stable atmosphere, and chemical imbalances that suggest something is actively maintaining them. These are not arbitrary preferences. They are clues drawn from the only example of life we know, Earth. Yet what makes the search fascinating is not certainty, but tension. Every promising signal has an alternative explanation. Every discovery raises new questions. Life does not announce itself loudly across the cosmos, it whispers, if it speaks at all. Learning to recognize those whispers is one of the greatest scientific challenges of our time. Why water matters so much. Water occupies a special place in astrobiology not because it is rare, but because it is uniquely effective. It remains liquid over a wide temperature range, dissolves a vast array of chemical compounds, and supports complex molecular interactions. On Earth, water is the medium in which life's chemistry unfolds. From a scientific perspective, water is not a guarantee of life, but it is a powerful enabler. It allows molecules to move, react, and organize. Without a liquid medium, the chemical pathways that lead to biology become far more constrained. This is why planetary scientists pay such close attention to any evidence of liquid water, past or present. River channels on Mars, subsurface oceans on icy moons, and atmospheric water vapor on exoplanets all carry weight far beyond their physical presence. They are signals of possibility. However, water alone is not enough. Earth itself remained lifeless for hundreds of millions of years despite abundant water. Life requires time, stability, and the right chemical environment to emerge. Oceans without sunlight, expanding the definition of habitability. For much of the 20th century, scientists assumed that sunlight was essential for life. Photosynthesis seemed fundamental. That assumption was shattered in the late 1970s with the discovery of deep-sea hydrothermal vent ecosystems. In the crushing darkness of the ocean floor, entire communities of organisms thrive without sunlight. Instead, they rely on chemosynthesis using chemical energy from Earth's interior rather than solar energy. These ecosystems demonstrated that life could exist in isolation from the surface, powered by geology rather than starlight. This discovery had enormous implications for astrobiology. It suggested that worlds with subsurface oceans hidden beneath ice might be viable habitats, even if their surfaces are frozen and hostile. Moons like Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, are now considered among the most promising places to search for life within our solar system. Both are believed to contain global oceans beneath icy crusts, kept liquid by tidal heating. When spacecraft observed plumes of water vapor erupting from Enceladus, containing organic molecules, the case became even more compelling. These moons do not merely contain water, they may contain the chemistry and energy gradients life requires. Atmospheres, more than just air. An atmosphere does far more than provide air to breathe. It regulates temperature, shields the surface from harmful radiation, and acts as a chemical reservoir. For astrobiologists, atmospheres are especially valuable because they can be studied remotely. When scientists analyze an exoplanet's atmosphere, they are effectively reading its chemical balance sheet. Certain gases persist only if something continuously replenishes them. On Earth, oxygen is the most famous example. Oxygen is highly reactive. Without constant replacement, it would quickly bind to rocks and disappear from the atmosphere. The fact that Earth's atmosphere contains abundant oxygen is a direct consequence of biological activity, primarily photosynthesis. Methane is another intriguing gas. On Earth, it is produced largely by living organisms. Methane and oxygen together represent a state of chemical disequilibrium. They should not coexist for long without active processes maintaining them. This is why the simultaneous detection of oxygen and methane in an exoplanet atmosphere would be so provocative. It would not prove life, but it would demand explanation. Biosignatures and the problem of false positives. The term biosignature refers to any observable feature that could indicate the presence of life. These can include gases, surface patterns, or even temporal changes in a planet's atmosphere. However, the challenge lies in interpretation. Nature is inventive. Many processes can mimic the chemical signs we associate with biology. For example, ultraviolet radiation can split water molecules, producing oxygen without life. Volcanic activity can release methane abiotically. Stellar interactions can alter atmospheric chemistry in unexpected ways. This means that scientists must be extremely cautious. A single gas is rarely convincing. Instead, researchers look for combinations of signals, patterns over time, and consistency with planetary context. This careful skepticism is not pessimism, it is discipline. The discovery of life elsewhere would be one of the most significant events in human history. It must withstand extraordinary scrutiny. Learning from Earth's deep past. One of the most useful laboratories for astrobiology is not another planet, but Earth's own history. For billions of years, Earth's atmosphere looked nothing like it does today. Oxygen was once a trace gas. Life existed long before it became detectable from space. This has profound implications. It suggests that many living planets might appear lifeless to our instruments not because life is absent, but because it has not yet transformed the atmosphere in obvious ways. In other words, we may be surrounded by inhabited worlds that are chemically quiet. Understanding Earth's evolutionary timeline helps scientists avoid narrow assumptions. It encourages the development of detection strategies that are sensitive to subtle, indirect signs of life rather than dramatic, modern Earth analogs. Technological tools for reading alien atmospheres. The ability to detect and analyze exoplanet atmospheres is one of the most technically demanding tasks in astronomy. It requires exquisite precision, stability, and sensitivity. Space-based observatories are particularly valuable because they avoid interference from Earth's own atmosphere. By comparing spectra, essentially chemical fingerprints, scientists can identify specific gases. Next-generation telescopes are designed not just to detect planets, but to characterize them. They will be capable of measuring atmospheric composition, mapping temperature gradients, detecting clouds and hazes, observing seasonal changes. These tools bring us closer to answering not just whether a planet could host life, but whether it does. The search for non-Earth life chemistry. While water-based life is our primary focus, scientists are careful not to assume that Earth represents the only possible biological template. In environments radically different from our own, alternative chemistries may be viable. For example, on Saturn's moon Titan, liquid methane and ethane exist on the surface. Some researchers have explored whether life could emerge in such conditions, using different solvents and metabolic pathways. This line of inquiry remains speculative, but it serves an important purpose: it prevents conceptual blind spots. If we search only for versions of ourselves, we may miss entirely different forms of life. Astrobiology, at its best, balances imagination with restraint. Why chemistry is the bridge between worlds. Water, atmospheres, and chemical signatures form the bridge between astronomy and biology. They allow us to connect distant points of light to processes we understand and some we do not. These elements are not proof of life, but they are prerequisites, context, and evidence of ongoing activity. They narrow the field from billions of planets to a smaller set of compelling targets. And they guide the development of future space technologies. Missions are designed around these questions. Instruments are built to detect these signals. Propulsion systems are optimized to reach worlds where chemistry hints at biology. In the next part of the series, we will turn from the what to the how. Even if we know where to look, reaching and studying these worlds requires new ways of moving through space. Chemical rockets, powerful as they are, may not be enough. To explore the universe deeply and sustainably, humanity must rethink how it travels beyond Earth. Why chemical rockets are reaching their limits. For more than half a century, chemical rockets have carried humanity's ambitions into space. They lifted satellites into orbit, sent astronauts to the moon, placed robotic explorers on Mars, and propelled probes to the edges of the solar system. They are loud, violent, spectacular machines, icons of technological triumph. And yet, for all their power, chemical rockets are nearing the edge of what they can realistically achieve. This is not a failure of engineering. It is a consequence of physics. To understand why new space technologies are necessary, we must first understand the quiet, uncompromising limits imposed by chemical propulsion. These limits are not matters of budget or political will. They are rooted in energy density, mass ratios, and the unforgiving mathematics of motion. How chemical rockets actually work. At their core, chemical rockets operate on a simple principle: expel mass at high speed in one direction to move in the opposite direction. Fuel and oxidizer react chemically, producing hot gases that rush out of a nozzle. The resulting thrust pushes the rocket forward. This method is extraordinarily effective for escaping Earth's gravity. Chemical reactions can release large amounts of energy very quickly, producing immense thrust over short periods. That explosive power is precisely what makes launch possible. But it also reveals the first limitation. Chemical rockets are optimized for short, intense burns, not sustained acceleration. Once the fuel is gone, the rocket becomes an inert object coasting through space. There is no gradual buildup of speed, just one dramatic push and then silence. This approach works well for reaching orbit. It is far less efficient for long-distance travel. The tyranny of the rocket equation. The fundamental constraint on chemical propulsion is captured by a deceptively simple formula, the Tsiolkovsky rocket equation. It relates a rocket's change in velocity to the exhaust speed of its propellant and the ratio of its initial mass to its final mass. The equation reveals a brutal truth: to go faster, you must carry exponentially more fuel. Every additional kilogram of fuel requires more fuel to lift it, which in turn requires even more fuel. Very quickly, payloads shrink while fuel tanks grow. At some point, adding fuel becomes self-defeating. Chemical rockets have already pushed this equation close to its practical limit. Even the most advanced designs achieve exhaust velocities constrained by chemical bond energies. There is no breakthrough waiting to be discovered here, only incremental improvements. In other words, chemical rockets are not going to suddenly become 10 times better. Physics does not allow it. Speed, time, and the cost of distance. When traveling in space, speed is time. A journey to Mars using chemical propulsion typically takes 6 to 9 months, depending on planetary alignment. Missions to the outer planets take years. Probes to the Kuiper Belt or beyond require decades. These long travel times impose severe constraints. Spacecraft must survive extreme environments for years. Electronics must function without maintenance. Human missions become biologically and psychologically risky. Mission costs escalate dramatically. For robotic probes, long travel times are inconvenient. For human explorers, they are potentially fatal. Extended exposure to radiation, muscle atrophy, bone loss, and isolation all compound with time. Chemical propulsion does little to address these challenges. Once the engine shuts down, the clock keeps ticking. Payload penalties and mission design. Because chemical rockets demand such high fuel mass fractions, payload capacity is always limited. Engineers must make difficult trade-offs between instruments, shielding, power systems, and redundancy. This constraint shapes entire missions. Scientific instruments are miniaturized, redundancies reduced, and ambitions scaled back. Every gram matters. When missions fail, they often do so because there was no margin, no extra mass for additional protection or backup systems. As exploration goals grow more complex, this mass penalty becomes increasingly restrictive. Sampling subsurface oceans, returning materials to Earth, or sustaining human habitats all require heavier payloads than chemical rockets can easily accommodate. The Earth-centered architecture problem. Chemical rockets are especially inefficient when used repeatedly from Earth's surface. Escaping Earth's gravity well requires enormous energy, and that energy must be delivered all at once. This has led to an Earth-centered architecture for space flight. Launch everything from the ground. Carry all fuel from Earth. Accept high costs and limited frequency. This model works for occasional missions. It does not scale well. As long as every mission begins with a massive chemical launch, space exploration remains episodic rather than continuous. It becomes an event, not an infrastructure. A truly spacefaring civilization requires systems that operate in space, not just from Earth. Reliability versus flexibility. Chemical rockets are remarkably reliable once launched, but they offer little flexibility after the fact. Trajectories are carefully planned months or years in advance. Course corrections are minimal and costly in terms of fuel. If something unexpected happens, an instrument failure, a new scientific opportunity, or a hazardous environment, the ability to adapt is limited. Future exploration will require more dynamic systems, spacecraft that can change destinations, adjust speed gradually, and respond intelligently to new information. Chemical propulsion is poorly suited to that kind of adaptability. Human exploration, a breaking point. The limitations of chemical rockets become most obvious when we consider sustained human presence beyond Earth orbit. A human mission to Mars using chemical propulsion would involve long transit times, massive life support requirements, significant radiation exposure, limited abort options. Even with perfect execution, such missions push human endurance to the edge. Adding safety margins quickly becomes impractical due to mass constraints. This is not a question of bravery or motivation. It is a logistical reality. To make human exploration beyond the moon routine rather than exceptional, travel times must shrink and payload flexibility must increase. Chemical rockets alone cannot deliver both.